So, hello back to our NLP for IS course. Uh, this is, I think, Unit 8 of our course, and this time we will have a look at fastAI for NLP. And this is what we'll do in this unit. The next unit we'll look at fastAI. This unit start with the basic ideas and how to do simple classification of text. And next unit we'll look at more complex things like applying state-of-the-art classification using transformer models from inside fastAI. So yeah, I'm using the given notebooks which are on the original fastAI course, which is online. And I'll just take some of those and slightly modify them for our purposes. The main goal here is to make it a little bit easier to digest and just focus on the NLP parts. I highly recommend, which is also here in the first box of the slides, to have a look at the original fastAI course, because I think it's very good and it gives you a more detailed introduction to using fastAI and deep learning in general. So, but let's start from the beginning of what I put into these boxes. So this is one of the lessons, the first lesson from the fastAI course, and I'll just at some points make some extra description in there for our purposes, which I highlight with three horizontal bars in the beginning and at the end of the cell, so that you know that this is the cell which I entered myself. Everything else is from the fastAI course. Okay, so what will we do in this unit? So we'll have an introduction to fastAI with a simple example, first from computer vision. But the process is the same like in NLP, and then we'll have a look at an example in NLP. So what is fastAI? fastAI is a library to get state-of-the-art results with very little effort and coding as compared to libraries like PyTorch or to TensorFlow. So it's like a wrapper or like an abstraction layer on top of PyTorch, and it adds a number of additional tricks to make training easier and more successful to get to state-of-the-art results. Okay, as I said, there is a great online course from fastAI, which is which you find here with this URL, with this link. Which I highly recommend to watch. It's a bit longer. It's for the basic introduction. It's I think 7 videos, and each video is 2 hours. So it's but it gives you a very good introduction, not only into NLP but also into computer vision, into working with tabular data, with recommendation. To do recommendations with artificial intelligence. So it includes different deep learning and AI fields. Okay, so how do we now start? What you should do to use fastAI, I mean, you can use it on your own machine but you probably need to have a GPU for it all a little bit bigger problems, so you cannot run it on the CPU. So either if you have a machine with a CPU, you can just install it on your own machine, or you can just use Colab, which I'm also doing here, to just make it easier. So what you do, you go to Google Colab, to open this notebook here, but you don't have to open this notebook. You can just open the original notebook from the fastAI course. So how do you do that? You say, so when you are in Google Colab, you go to File. So I should add here File, but I'll just show it. File, Open Notebook, and then you select GitHub, because the fastAI, all the fastAI notebooks are on GitHub. So, and there you can now search for fastAI. hit the search icon, and then you select, there are different repositories. You want to have the course version 3. The course version 4, they're just preparing it, but it's not online yet. So we use the notebooks from 3, and in 3 you find this lesson 1 pets notebook, which we are using here. So I don't open it again now because I've already have it open and I have it modified a little bit. But for you, you just open this notebook and can then start working from that notebook if you want to copy what we're doing here. Okay, so when you have the notebook open, that's this step of the installation. Then what's very important, don't forget to turn on GPU support for the notebook, else training will be very, very slow. So you go to edit, you can scroll down a bit, edit notebook settings, and then I have already turned it on. By default it will be none, but you definitely want to have it on GPU. I didn't try TPU yet, so GPU should be fine. Maybe TPU works. I've heard last semester that some students said that it was not accepted for them to use the TPUs. So GPU is fine. Save, and now we're all set to start. Okay, this was my first introduction cell. Now we can go to the original notebook, which is starting here. So there's some welcome stuff. Yeah, it's just some explanation. You can have a read. And then we look at the cells which are in this notebook. So the first cell, and I just run all the cells while we go along. The first cell is just to tell the system to reload modules if they change in the background, and to do plotting of images in line inside the notebook. So this is just some configuration stuff. Then in the next cell we import the library, and yeah, which for convenience we just import everything from the Vision sub modules of fastAI. Yeah, as it says here, fastAI is built on top of PyTorch. So to change the library, then you will often need to, yeah, it will be it's based on PyTorch, so you will use PyTorch in the background if you want to change the source code, just to let you know. Then another important thing for all learning problems is to set the batch size. If you set a higher batch size in training, I think I'll explain a little bit later batch size, what it means, or maybe we already explained it in PyTorch, in the PyTorch videos, I guess so. So if you have running out of GPU memory, so you can even see it in here with RAM. If you're running out of GPU memory, I think you'll get an error message just popping up. So you know the first step, what you can do is just reduce the batch size to a smaller number. Then the learning takes less GPU. Okay, so we run this cell. So this is just basic setup, which we did so far. Then which data will we look at in the first video? It will be a data set about pets, about animals. So it's about different types of dogs and different types of cats. And we have in this data set images, so it's based on images. Next we will do text, but it's just the same idea, and this one is even easier, this notebook, just to start. So we have 12 different types of cats and 25 different types of dogs, so 25 dog breeds. And we want to classify, when we get a new image, what kind of the cat or what kind of dog is it. It's based on some academic data set, and in 2012 the best accuracy was around 59%. So let's see how far we get. So the first step is just to download the data. So there's a function in fastAI which you can use for the built-in datasets. So fastAI has a couple of datasets which are already built into fastAI, so they're even easier to use than external data sets. It's a bit like with NLTK, which had the books corpus and many other corpora built into NLTK. So there's a function, it's called untar data, which we just, with help function name, we can just get a description of what the function does. One nice thing about fastAI is that they always, for the functions, they provide the type of things which of the parameters. So this function, it expects a URL where you download the dataset from. It's of type string. The file name. So this is then, I think the rest is optional. So you accept the URL, which union means it's either a path or a string. I guess is then where the data that will be downloaded should be saved, but you can just use the defaults and so on. So we have this function. Then, okay, now we finally start to do something, which is download this dataset. So now it's downloaded from some Amazon cloud servers, and we wait until it's finished, or we can just go to the next part. So this is then saved. This gives you back a path object, a Python path object, so you know where the data is. Then we can run ls on the path to see where it now saved this data. Maybe we can already see it here in the files. Sample data. Okay, because it's saved in root.fastAI, so we don't have to care so much about where it's saved at the moment. We already have it in the path object. So how to close this? Okay, like that. Okay, so but what's more interesting, after downloading the dataset, now we see we have a folder of images where the images are in, and a folder of annotations. So these are the two basic things which we need in supervised machine learning. We need the data itself, and we need the labels for the data. Okay, so when we have done this first step of downloading the data, we need to understand how the data looks. This is then described in this paragraph here. I recommend you to read it. But it's very clear in all machine learning. The first step is what you need to do is to understand the data, how it's structured, where the labels are, what is inside, to be able to learn for your problem. So the basic three steps also in fastAI, they're always loading the data in. Here you load it into some internal data structures for fastAI, which can then be used in step 2 for training. So step 2 is the training process, and then step 3 is to evaluate your model and maybe to use it for prediction in a production environment. So for the first step of loading the data now into the fastAI objects, which can then use the data into for training. So what do we need to do? So now we have downloaded it. So now we want to find out what files are there. So this is in this step. We just, oops, maybe I didn't do this yet. So we made the paths, which will then be used in the next step. So here we just get a couple of, here we load from the path where the data lies, the path for the images. We load the image files into a list of file names, and we show the first 5 file names here in this output. So now we have the list of images which we use for training and for validation for our training set, for our data set which we use in the deep learning process. Okay, then here this data set is a bit specific in the sense that we don't have labels somehow in some external file, so where the labels are, but we just have the labels inside of the data itself. because as you can see, you have the images and the labels are inside the image path. So we have the label of what type of dog, or this is Bengal, is probably a cat, what type of animal, cat or dog this is, we have inside the label. So if we only have it in this form, then the question is, how do we easily get the label outside of the out of the path? So in this case, he uses Jeremy Howard a regular expression to detect the label from the path. So if you have ever worked with regular expressions, I hope so, then you can maybe already understand or have a look at this regular expression. So here in this regular expression, how do we find the label in there? So in all paths, we have at the end of the path, we have JPEG. Then we have some number, which is the \d. Plus just means a 1 or n numbers, like 64. And after that we have the dot, so which is here. Oops, I didn't want to break it. Okay, so now we have covered this last part. Then we have the underscore before that, and before this whole thing we have the label, and it's everything which is not a slash, because the slash here it's not part of the label. So we want everything between the slash and this last part which we had from there. So we want the Bengal part in there, and for this we just collect all characters which are not the slash before this last part. So this is basically what the regular expression defines in here. Okay, so the next step, or now the main step, this was just downloading the data and setting up the paths where the data will be found, is to create this data loading. It's called data bunch in fastAI, so this object which will store the data and will then be used in training to handle the data. So it's here called, it's an image data bunch, so it's a couple of images as our training set, and as we want to use the regular expression to get the labels, we use here this from name regular expression function for this. So as we'll see in this video, and then for the NLP loading in fastAI, there are many functions depending if it's you have the labels in a file, or you use a regular expression to extract the label from a file name. You can use different functions. So there you have to look a little bit at the API description of fastAI on how to do this. There are two different ways, but for the details, look at Jeremy's videos. There's the data block API, and there's this data bunch objects to load the data. So here we use the simpler form of using this data bunch objects. Okay, so what do those data bunch objects get as parameters? They have the path where to find so this is just the path where in the file system the file names are. Then we have the list of file names. Then we have these patterns to detect the labels out of the file names. And then we have a couple of more things like transforms, which just does data augmentation. So it takes and some things like these. For example, it takes one image of this dog here, Boxer, and rotates it a little bit and maybe flips it side by side and does different things like this, and puts all of that into the training set. So it has more training data, which is always helpful in deep learning or in machine learning from augmenting the data. So it may also change colors in some way and stuff like that. So this is what the transforms do. Then we have to define an image size for the images to be used for the learning process. And finally, we have give it the batch size, and we have to normalize, call this normalize function, which we will discuss in more detail later. It's a bit more, not more advanced, but a little bit more advanced. So what you need to do for the first understanding, or what you should understand now, is just to load the data, and then we can look. Oops, I didn't do it yet, so it doesn't work, obviously. So we run these cells, and once the data is loaded, we can look at some example images from this data bunch which we created. So with this function show batch, how many rows we wanted to see. We have 3 rows now in the output, and what is the size of the figures. We can see some example images plus their labels. So just to see that we loaded the data correctly, we always want to do this so there's no mistake. That seems like the labels make sense. So bang, I'm not an expert in cats or dogs, but it's definitely cats, and yeah. So it seems like the basset hound is, so the labels make sense, so everything was done correctly so far. Then we can see which classes we have in our data set and how many classes that is. So in data.classes, so data is the object which we created here for the data bunch. We see how many classes we have and which classes we have in the data set. So it's in total we have 37 classes, so it's quite a difficult problem if you get those those images, and you need to classify them into 37 different breeds, which some of them look very similar. Good, now we can continue with the next step, which is the training. It's maybe the most exciting step, although often the data loading is the more difficult step in a sense, to get the data inside the model. Once you have it there, often the training is not so hard to do, especially in fastAI, where you use existing models, usually use existing models, pre-trained models, and just use transfer learning to retrain those models on your data. So how does it work? In this case, we build it, we use ResNet, which is a CNN. I think you already learned about CNNs in the machine learning courses at ITMO. So CNNs are often used for images, as you probably learned. So we built on ResNet 34, which is a 34-layer convolutional neural network. And we use this for our so we don't define the architecture ourselves. It's not necessary. We can just use a very successful and very good architecture and build on this. So in the first step, so this is the first cell, we define our learner object, which is a CNN learner, because we use a CNN. Then we tell this learner object the data which it should use. So this is just the data bunch object which we created in the previous steps. Then we have to tell it which model we want to use, and as I said, we use this ResNet 34. So here it downloads both the model itself, it gets the model itself, the architecture, and it downloads, as you see here in this 33 megabyte, the weights, so the pre-trained weights for the model. And then we have to define an error rate metric, and for the metric which is shown to the user when we train, we use the error rate. So this is not the loss function or the which we use, but it's just a metric which is shown to the user in the training to see how the model learns. One more word to the model. So we use this ResNet. So in all our examples here, we want to use transfer learning because here we can just build on some large pre-trained models, which very much helps us to get a good accuracy on our data set. Because the model does not have to learn everything from scratch, which it would have if we use random weights to initialize the model. but we initialize the model with some pre-trained from some pre-trained data. And this ResNet 34, it's has been trained on the image dataset. I forgot the name. So the large image dataset with I think 1.5 million images in there. And it knows a lot about classifying images. So, and in this image dataset, as I remember, there are 1,000 or so different classes of all kinds of objects. So there will definitely also be some animals in there, but it will not be so fine-grained like it will be in our task, which we have now. But still, it's a good starting point to have a model which can already understand images very, very well. Okay, so then if we want, we can just show how the model architecture is. So as we scroll through there, it's a large model of, as I said, 34 layers. With different convolution layers in there, and then batch normalization and ReLUs and blah blah blah. But we don't need to have a look at the model architecture now, we just use it. Okay, so once we have the model initialized, we can already start learning. So this is the next step, which I can call here. So we call this function fit1cycle. And the parameter here, it's just how many epochs we want to learn. So now this obviously takes some time, because now we're learning, and based on this large ResNet model with our images, which we're now using for the learning. Once the learning is finished, we can then save the results, so this learned model, to some name. So we can then just, next step, we don't have to learn it again. We can just load this stage 1 model and maybe continue learning on this, or we can just just use it how it is. Okay, good. I'll pause the video until the learning is finished. Okay, so while the model is learning, it's a good time to get some coffee, or maybe in Russia some chai or mors or whatever you like to drink, like I do, and it's almost finished, so we can already start looking at the next step. So the next step, once it's learned, you want to look at the results you got, obviously, and see what is the quality of the results. So let's just start looking there. In fastAI they have some built-in classes, some objects which you can use for looking at your results, but you can also just look some scikit-learn or use scikit-learn or whatever for building those kinds of output matrices. So, but it's easier to use the built-in stuff here, which is one thing. It's called classification interpretation. You give it this learner object which you just trained, and you get some interpretation object from this. And from this object you can for example then get the top losses, which just means get the example from the validation set. I think it's not from the training, but from the validation set, which have the largest losses, so which were classified the most wrongly to the most worst. So they have the highest loss, so with the prediction and what is in the data set is very far away for those. So these are like bad classifications. So you can get some of those, and then you can print those. So, but let's first look if our training has already finished. Okay, so now we see it has trained for some time, maybe 3-4 minutes. I think it said somewhere how long it. Yeah, it just says here. So about 5 minutes, 4 times 120. You can see the epochs, you can see the training loss, the validation loss, and the error rate. So a couple of things to note here. If the training loss is higher than the validation loss, then you're definitely underfitting, which means you need more training. But it's at the start of the training that is expected that so that you need more training. Then the training loss and the validation loss go down. At the end, it's still that the training loss is higher than the validation loss. So you could definitely train this model more, which we'll do later, to get even better results. And then we can look at the error rate. So at the start we have 11% of images were classified wrongly. Everything else, and there are 37 classes, so it means that 79% of the images were already classified correctly into those 37 classes. So very difficult problem after only 1 minute of training. So this is really great, and this shows you the power of using transfer learning. This is only possible because we use this big ResNet model, which is trained on this large collection of images, so which is very good at looking at images from the start, and we just fine-tune this model, and it's only possible to get to this accuracy so quickly, especially in this short of time, using this transfer learning idea. And I think it was said in the beginning that in 2012 the state of the art in research was 52% of correct predictions, and now 2020, there you can see the advances in deep learning. Now we have 89%, so 11% errors, 89% correct predictions after 1 minute of training, and then it was 52% after a long time of researchers trying to optimize the model. And at the end we have 7% errors, so we have 93, around 93 or 92% of correct predictions after only 5 minutes of training. So let's have a look at a couple of those predictions. So here we only print the bad predictions in the top losses, but let's run this stuff. Run. Okay, we will see it will maybe be the same images or some other images. Maybe you have some random changes, which we get if we run it again. Okay, now we have a little bit different images from what was in the original notebook from fastAI. Okay, so we see the wrong predictions were, for example, this one. So this was, so you can see how is the semantics of this string. So it's first is the prediction, then the second one is the actual, and the third one is the loss, and the fourth element here is the probability. So the prediction was Samoyed dog. I've never heard about this dog type or breed, and it was so the prediction was Samoyed, but it should have been Great Pyrenees. Okay, so and it was wrong prediction. Let's look at the second one, because those dogs are maybe a little bit more similar to what people know. So it was predicted as Basset, and actually it's a beagle. So let's maybe see if Basset and beagle look very similar in real life. So and here also the dog, it's a little bit covered behind this basket, so it might be even more difficult to predict. So Basset dog. Okay, Basset looks like this. Okay. Bit ugly. And the other one was beagle. Beagle dog. Okay, so they are actually quite similar from their colors. These are all babies, I think. If they are grown up, then they really look quite similar with this white and brown around the eyes. So it's probably different, not so easy to keep them apart. So it's understandable why on some of the images we have mistakes. So where is our notebook? Here it is. Okay, so other errors which we get: American Pit Bull, Basset. So it was this one was predicted as Pit Bull. Maybe it's because of the angle, because here on this it looks a little bit like more like a pit, not more like a pit bull, but closer to pit bull than and Bassets normally you look like. This is predicted as bulldog, but it should be boxer. I think those dogs also look a bit similar. Bulldogs and boxer. Or here you have Chihuahua and Pinscher, which are both very small dogs for Kim Kardashian and girls like that to put in the handbag. So yeah, they maybe also look a bit similar. So we can see why there are some mistakes on some of the cats. Dogs. Let's look at one cat. Oh, Russian blue. So there's some Russian type of breed, Russian blue, but so it was predicted as Russian blue, but it should be Egyptian Mao. Mao. So let's see how Russian blue looks like. Russian blue cat. Okay, it's a gray cat. Yeah, quite pretty. Seems to have rather large ears. At least when they're babies, but it's probably for all baby cats. Okay, Russian blue and okay, just last one. Egyptian Mao. Okay, they're also gray, but the difference seems to be that the Egyptian ones, they have some little, yeah, like sparks, like dots on their fur, which are black, or some stripes. And the Russian blue, it seems to be like looking the same, but only gray or silver color. Yeah, and on this one, yeah, you cannot see the stripes so far. It might be just from the sun. So yeah, maybe that's why it was difficult to classify this one image. Okay, so you can see there are some errors still, but we have 92% of correct predictions already after 5 minutes of training. So it's really great. You can look at the documentation of stuff in fastAI very easily, either with the help, but with help I think you only get the parameters which a function has, or you can use the doc function, and it gives you some more documentation about any function which you want to use, or you can just have a look at it like that. So this gives you like the doc string and some explanation, and the more interesting thing is you can look at the source code. So open it in another screen, so you can go directly to the source code of the function, and if you really need to understand something about the function, you can just look inside the source code. And fastAI guys say that their functions are usually not so, I mean, this one is maybe a bit more complex, but it's usually just a couple of lines of code. So here it's already ended. So it should be not so hard, maybe now in the beginning, yes, but later, if you really want to use this in somewhere, to understand the source code and even change the source code of the fastAI library. Okay, then one more thing, confusion matrix. I think you already probably all know what a confusion matrix is. So here we just have the actual predictions, and on this axis the not the actual predictions, the actual the ground truth, what it really is. On the y-axis and on the x-axis you have the predicted values. So, and as you can see in the confusion matrix, actual and predicted, it's in most cases it's the same. So this is what we want, but we have some cases, for example, the actual Egyptian Mao was in 9 cases predicted as the second column as Bengal. So we have some errors there between Egyptian Mao and Bengal. And we have one error on Egyptian Mao versus Abyssinian cat. Okay. That's one way of looking at it, and the last way of looking at it is a function. It's called most confused. And it just gives you the classes which were most often being confused against each other. So Egyptian Mao and Bengal has 9 cases, and Pitbull and Bull Terrier, so American Pit Bull and Staffordshire Bull Terrier have 7 cases. So probably if you look up those kinds of breeds, they maybe look very similar, so it's hard to distinguish between the two, and this is where the model also struggled from the photos sometimes to distinguish those classes. Okay, this is the basics of how to train a model and how to evaluate it. One last thing which we want to have a look at on this notebook is how to unfreeze a model and train it even more, and I'll explain in a second what that is. What's also in this notebook is then how to train on a bigger ResNet. So there's also ResNet 50, which has 50 layers in the deep learning model, which might get you a little bit higher accuracy. So maybe 1% or whatever. If you have like 8% left, which you could improve, you can try. If you really want to go to the edge of accuracy, you can use other models and work on bigger models or whatever kind of things to try to fiddle around to improve the results. Okay, so let's look at on this notebook on this. Let's look at this last part for us. What we did now when we just used the pre-trained model. What was done by fastAI, it just added a couple of layers at the end to the model, and then some softmax layer, I guess, for using for the classification. So it was just adding a few layers, I don't know how many, maybe 3-4 layers to the 34 layers of the existing model. So just a little bit, which was then fine-tuned, which was then trained, let's call it that way, only those couple of layers to do the final prediction. So we had the large layer of 34 layer, the large model 34 layers which were not changed, and they are already very good at predicting all kinds of images. So then we used the output of this and put it into 3 or 4 or whatever layers additionally, and those layers learned to distinguish the different cat and dog breeds. Okay. But what we want to do now to maybe even get better results, to train the whole model, not just the last couple of layers. And this, to do this, we need to unfreeze, it's called, just to make the weights trainable, to unfreeze the model, and then we can train some more and see what happens. Maybe here we're training only for one epoch, so maybe that's not enough, I'm quite sure, but to get the best results, so probably if we would set here fit one cycle 10, but it would take a much more time, then we probably get, and we would see how what happens if we train more. But okay, there is more training coming. Okay, this is just like a first. We train it for one epoch here, and then we look at the learning rate. That's also one important concept which we look at in a second. The learning rate we want to use in training the next steps. Okay, let's make a short break. No. Okay, training is finished of this first epoch here, and we can see that even the learning rate and the loss and everything got worse now. And that's something that might be expected because we're now updating the whole model, and it just needs some more training to again get to some good results now, because now the weights maybe they changed into a direction, obviously, which was not very helpful, but this just a little bit of training on the whole model. So we trained it, we save it, and then we want to train it some more, and for this now we want to see what is the best learning rate to train this model some more. And the learning rate is there were some very good explanations also in the fastAI videos by Jeremy Howard, so I recommend to look at that, but in short words, and I think we already discussed it, or you should know it, it's just how far you update. So you get some from the from the loss function, you get some gradients. The gradients is in which direction to change the weights to improve the model, and the learning rate is then how far you jump into this direction. And it's a very delicate thing, because if you use a small learning rate and too small, then maybe learning just takes too long, because you make very, very tiny steps into the direction which you want to go, and so it may take many epochs to get somewhere. If it's too high, but then it's even worse, then you jump out of you go into you jump so far that you get to worse places than you have been before. So the whole thing, it can be you can see it like a landscape. So you have some mountains and valleys, and if you want to go down into the valley, and you know which direction to go. But if you go too far, then maybe you go already up on the other side of the mountain, and you go up even higher than you are now. So to a higher place than you are now. So you can get to worse places if you have a bad learning rate. Okay. So it's takes some time to compute this. Oh, is it finished? Ah, yeah, it's already finished. So you get some kind of graph like this. So this is maybe the most difficult, not most difficult, but it takes the most experience to understand what learning rate might make sense now to use. Usually it's, and here we use even those slices. Okay, I will explain in a second also this, why we have now two learning rates, or the slice thing. So in this graph you have on the one axis you have the learning rate, and on the other axis you have the loss. And you can see from the learning rate finder some landscape. So you definitely don't want to use a learning rate in your training where the loss is getting worse. So everything around this area of so this is 1 divided by 1000. So 1 0 0, so 0.001. This learning rate you definitely don't want to use, so you want to use a smaller learning rate somewhere around here. One heuristic would be like go to the lowest part, which is around this area here, and then take a learning rate maybe divided by 10 of this lowest part, or before it goes up. So before it goes up is around this area, divide this by 10 and use this as a learning rate. Or another idea is often to look at the area where it's going down the steepest, like over here it's going down very steeply, so maybe you could use this as a learning rate for your algorithm. What is done here now in this step to use a range of learning rates between those two things which we discussed, or pretty much. So it's between 1 e to the -6, which is here, and here. What does this mean? Why do we have like a range of learning rates? We now have this large model of ResNet-34, which we use, and we want. And the first couple of layers in those models, maybe you've heard it from your other courses, or which is maybe common knowledge, they learn to recognize, to detect very basic geometrical things, or very basic objects. So in the first layers of your ResNet, maybe you detect lines, or like corners, or little boxes. And so in this you don't really need to update a lot, because it doesn't matter if you detect a cat or if you detect a car or whatever in your image, you'll still be interested in lines and colors and very basic structures. So you want to change the first part of your model less than the very last part of your model, the higher layers. And the higher layers, they finally lead up to the prediction if this is like this type of cat or the other type of cat. So what we do here, we say that we use learning rates between 1 divided by 10 to the 6 to 1 divided by 10 to the 4, depending on where we are. So the lower layers, we have a lower layer, the first layers in the network have this learning rate, so we just divide the layers up into like blocks, and we assign different learning rates to the layers. So this is all what I wanted to explain in this complicated way, and the last layers have a higher learning rate. So this is why we use this kind of thing here. Okay. And then we could learn again. So we decided which learning rate we're using, and we have a look at some other examples then in NLP on how to decide about the learning rate, because that's quite important, and it needs some experience to do that. Okay, so I let it train, but I don't need to wait until it finishes. So we can expect at least to get it as good as it was with the 7% error rate after we train it some time here. And then we could again, we could plot our losses. So this I can just show for what I did yesterday, I think, plotting these losses. So from the learner object, which now learned the model, we can see after how many steps or how many batches processed how the loss goes. So often maybe in learning it goes up in the beginning, because here, and I will see in the next graph why, and then it slowly goes down. One of the tricks in fastAI is to use this, it's called slanted, yeah, this kind, I forgot the word, I should know it, like I think slanted triangular learning rate. So it has been shown in research recently that if you first go up with the learning rate to the maximum and then over the time of iterations you go down again, it helps you to quickly find the good solution. Because in the first area here, you want to jump to somewhere in your lost landscape where the learning rate, or where there's some kind of valley which you want to find. You want to find the lowest point, so you want to get into some large valley, which you do here. And then once you're in a good part, you lower the learning rate to not jump around too much anymore. You don't want to jump out of this valley again, so you want to stay in there and then find maybe the best place inside this valley, slowly go in there with a lowered learning rate. And this is also why in the beginning here the loss goes up a little bit, because it probably jumped around in the landscape to places which were not really good because it was jumping around so far. But then it somehow finds some good places and then goes down. Okay, good. I think that's enough for the first video. In the next video we'll have a look at NLP.